Hello, this is Dr. Gardner. Today we're going to be talking about atomic mass units and how they relate to molecular formula masses. Then we'll scale those up to gram quantities as we consider much larger numbers of atoms, molecules, or ions or small particles when we talk about moles and Avogadro's number. This will allow us to determine molar masses for all the different substances we might want to analyze, and it will lead into determining chemical compositions of compounds in this chapter. To first understand this, we need to look at the unit that is the atomic mass unit. We will abbreviate atomic mass units as AMUs. We use atomic mass units to describe the masses of individual atoms or individual ions or individual molecules, which would be very difficult to measure actually in the laboratory setting. So we'll learn how to use these to scale up to gram quantities when we have a very large number of the particles in question. Now, first of all, if we consider our atomic mass unit is defined as exactly 1/12 the mass of a carbon-12 isotope. Okay. If we consider how this relates to other atoms, if I have a hydrogen-1 isotope, well, it's about 1 atomic mass unit. If we consider the mixture and nature of the hydrogen-1, hydrogen-2, and hydrogen-3 isotopes, well, our relative atomic mass would be 1.008 atomic mass units on average, whereas my option 16 isotope has an atomic mass units of 16.00 atomic mass units. I'm not able to measure these on the scale in the laboratory because it's not sensitive to measure a single atom or a single molecule, but we can study these with other techniques. For example, we can use mass spectroscopy techniques to analyze the mass of an individual molecule or atom, but most of the time what you're going to be working with is gram quantities in the laboratory, and so we're going to need a much larger quantity of the atoms or molecules. In order to scale atomic mass units up to grams, we're going to use a term called the mole. Now, a mole is a specific number of atoms that will help us add up to gram quantities and relate simply atomic mass units to grams. So for example, if I have 1 mole, spelled M-O-L-E, it probably originates for the original terms for molecule. It is the number of atoms or the number of particles that we would have that would add up to gram quantities that was equivalent to the atomic mass unit scale that we had for an atom. So for example, remember carbon-12 isotopes are 12 atomic mass units. If I have a whole mole of them, we've scaled that up to 12 grams. So if I have a mole of carbon-12 atoms, I have 12 grams. Okay, so just realize 1 mole of whatever my atomic mass units are for my mass of an atom or a molecule or an ion would scale up to that number of atomic mass units would scale up to grams if I have a mole quantity. So this is a very large quantity. In fact, it takes 6.022 times 10 to the 23rd of these atoms or molecules or ions in order for a mole quantity to be achieved. So what I'm saying is if I have a single carbon-12 atom, it would have an atomic mass unit of 12 AMUs. However, if I have 6.022 times 10 to the 23rd carbon atoms, well, that large amount scales up to 12 grams. But don't confuse the two. 12 grams is many more than a single carbon-12 atom, even though I could describe that single carbon-12 atom in 12 atomic mass units. It's a nice thing this number shows us that ratio as we scale up from atomic mass units to grams. We call this Avogadro's number. It was named for a scientist that helped lead us to understand that the chemistry of atoms and molecules existed. It was named in his honor. He didn't actually generate the number to begin with, but we might abbreviate Avogadro's number with an N subscript A. Okay, so I want you to just remember that you need to memorize this number, and so that's your goal. Before our next class period, I'd like you to memorize 6.022. If you memorize it to 4 significant figures, that will be sufficient for our calculations in the course, but it's 6.022 times 10 to the 23rd. That's a positive exponent on the scientific notation. That's a pretty big exponent, so that's a very large number. It takes a very large number of atoms or molecules to add up to gram quantities with respect to relating moles and grams. Now, first of all, if you're trying to understand what this number is, well, it's just a term that we use to count the number of objects in chemistry. Now, because our objects are so small when we're talking about atoms or molecules or ions, we need to count a lot of them to get to the gram size. In your everyday lives, you're used to using terms that relate to numbers of objects. For example, you're used to talking about dozens, maybe with respect to eggs or donuts, or you can talk about a gross sometimes when you're ordering things, which is going to be a dozen, 144, or you can talk about a pair, like a pair of gloves. You know a pair means 2. Okay, so we know a dozen is 12. We know a pair is 2. You're going to need to learn that a mole is 6.022 times 10 to the 23rd. It's just a much larger number that you have to remember, but the same relationship. We have to have such a large number for Avogadro's number because the particles we're talking about are so small and have so little mass individually. Okay, we're going to be talking about mole quantities of atoms, mole quantities of molecules, and mole quantities of ions in the course. Realize that if we can find the atomic mass unit weight of those atoms, molecules, or ions, once I scale them up to 6.022 times 10 to the 23rd of those objects, we end up with that same value that was in the atomic mass units, but now in grams once we have a mole quantity. So it's going to be very useful relationships. Now let's think about this. Would a mole of any object we were talking about weigh the same amount? Would it have the same mass, actually? Well, let's consider this. How much does any of these relationships we talked about, like a dozen or a pair? If I have a dozen eggs, does it weigh the same amount as a dozen donuts? Does a pair of gloves always weigh the same, depending on what pair of gloves we're talking about? They don't. It depends on the mass of the individual object we're talking about, doesn't it? For example, let's consider we had a dozen 200-pound football players. If I have a dozen 200-pound football players, if I want to know the mass of a dozen of those football players, well, I can do a simple calculation. I can say one football player weighs 200 pounds, multiplied by the number of football players in a dozen, that's 12, I end up with 2,400 pounds per dozen football players. Now this will be different. If I'm talking about a different object that weighs a different amount, I may still have a dozen of that object, but depending on the mass of the individual object, I may have a completely different overall mass. So for example, if I have one dozen 120-pound gymnasts, well, I can realize that 120 pounds per gymnast, one dozen is 12 gymnasts. We can see then 12 times 120 is 1,440 pounds. So I want you to notice that a dozen of one type of object is different in mass than a dozen of another type of object. This is the same as well for moles of items. So if I have Avogadro's worth number of items, their masses overall for that mole quantity will weigh different depending on the masses of the individual item. So for example, if I have 1 mole of 200-pound football players, well then instead of multiplying by 12 when we had dozens, we now multiply by Avogadro's number, so about 6.022. So 200 pounds per football player, there's 6.022 times 10 to the 23rd football players per mole, which is many more football players than on planet Earth. But we could calculate a mass. It would be 1.204 times 10 to the 26 pounds per every mole of football players. That's a huge mass that we're talking about. Now, if I have 1 mole of 120-pound gymnasts, well, if 120 pounds per gymnast, I can multiply by Avogadro's number per mole. We end up with 7.22 times 10 to the 25th pounds per mole of gymnasts. Notice that the mass for a mole of gymnasts is less than the mass of a mole of football players. That's because the individual object, the football players, is heavier than the individual object of gymnasts being lighter. So the mole quantities also scale up in a similar fashion, where the heavier objects have a greater mole mass and the lighter objects have a smaller mole mass. So we're going to talk about molar masses. A molar mass is the mass of 1 mole of an object in grams. What's nice is if we look at an object that we have the value on the periodic table for, like an atom, in atomic mass units, we can scale that up easily to grams. So if I have carbon-12 atoms, which have 12 atomic mass units each for their mass, if I have 1 mole of those carbon-12 atoms, I'd have 6.022 times 10 to the 23rd atoms. That's the same as 12 grams of carbon-12 atoms. So if I have a mole quantity, that would be my value in grams. Now, if I have 1 mole of carbon-12 atoms, just realize that's the same as having 12 grams of the carbon-12 isotope atoms. Now, in nature, I actually have some slightly heavier isotopes, so my mixture of carbon in nature would be 12.01 atomic mass units on average, so it would be 12.01 grams per mole if I had a mixture of a variety of the isotopes of the carbon atoms. So that's why I would report 1 mole of carbon atoms in nature as 12.01 grams of carbon, because it's not all pure carbon-12 isotopes. Now let's look at the periodic table. What is the mass in atomic mass units on average for the relative atomic mass of lithium? So if we look up at lithium, it has an atomic mass unit of 6.9412 for the average atomic mass unit. If we consider if I have a mole quantity, what would be the gram amount of that? Now remember, the atomic mass unit for a single average for the lithium atoms masses would be, if scaled up to a mole quantity, the same value in grams. So I'd say 1 mole of lithium atoms was 6.941 grams of lithium. So for any element that we look for it on the periodic table, the atomic mass and atomic mass units would equal the molar mass in grams if I have Avogadro's number worth of those atoms. 6.022 times 10 to the 23rd atoms will give me that mass in grams. So for example, if I wanted to know about, let's say, nitrogen. So if I had a mole of nitrogen atoms, its mass would be just above 14 grams. Okay, however, we know nitrogen exists as diatomic molecules in nature, so if I have diatomic nitrogen N2, which would have a mass of around 28 atomic mass units, it would scale up, if I had a mole quantity, to about 28 grams. So be careful when you have a diatomic element. They often exist in packets of 2 in the molecular form rather than individual atoms in chemical reactions. So be cautious with that. Now, the reason that it's very useful to work with mole quantities is that I can weigh the grams out in the lab. For example, if I have a mole of sulfur, well, then I'm going to have about 32 grams of sulfur, and it would fill a 50 ml beaker up to about this height to weigh it on the lab. Now, if I have a mole of magnesium would be about 24.3 grams per mole, and it would fill a beaker about this full. If we have a mole of tin, well, my tin's going to be about, if we look on our periodic table, about 118.7 grams per mole. A mole of tin would fill a 50 milliliter beaker about this high. If we look at copper, about 63.5 grams per mole for copper. It would fill up this much of a beaker. If we look at silicon, if we consider silicon as about 28 grams per mole, we end up with a beaker filled about this full with 1 mole of silicon. So we can see mole quantities are fairly simple to weigh out in the laboratory, or even if we measure a fraction of a mole, we can weigh them out in the laboratory on scales, fill our containers with them. They're very useful for handling and manipulating molar quantities. Now, a lot of times we'll be talking about what are called molecular masses, also known as formula masses. Sometimes you might hear them called molecular weight or formula weight, but we'll try to call them masses in here. We also talk about molar masses. Now, a molecular mass would be the sum of all the atomic weights of all the atoms in the molecule. We could report that for a single molecule in atomic mass units, or if I had a mole of that molecule, we would report it in grams per mole. Okay. Now, the nice thing about calculating molecular masses is it's fairly simple to do so. We can go ahead and go to the periodic table, and we can go ahead and find how many atoms of each type are in the molecule. Take the atomic weights from the periodic table times the numbers of those atoms, and then we can add up the total, which I'll show you here in a moment. Now, a formula mass would just be the sum of the atomic weights of all the atoms in a compound formula. Okay, so the difference here is not all substances exist as molecules. Remember, when my nonmetals combine and they overlap their outer orbitals to form covalent bonds, well, then we could talk about those as molecules with a molecular mass, but sometimes it would be better to talk about other substances like some ionic compounds which don't have individual molecules as a formula mass. Okay, so we're going to use these somewhat interchangeably as the masses of the substances we're talking about. Formula mass will work for either molecules or ionic compounds, whereas a molecular mass is suited more towards naming the masses of molecules. Now, if I have a mole of whatever substance I'm looking at, once I've found its formula mass or its molecular mass in atomic mass units, if I have a molar quantity, 6.022 times 10 to the 23rd, and yes, I meant that you should memorize Avogadro's number. So if I know there's 6.022 times 10 to the 23rd of those molecules, or that formula I'm talking about, I would have the same value for the mass in grams per mole. Okay, so let's consider sulfur dioxide. Let's find the molecular mass or molecular weight, and how we can do that is just remember it's the sum of the atomic masses and atomic mass units in the molecule. So sulfur dioxide, here we have a little space-filling model. It's a ball and stick model of sulfur dioxide. We can go ahead and look at how many atoms of each type we have in it. We have 1 sulfur and 2 oxygens, and you're going to find it's really helpful to draw out a little table like this. So you might be practicing this in your notes. Draw out a table of how many atoms of each type that you have. Okay, now the mass of each atom of each type. One sulfur atom, if I look on the periodic table, is 32.07 atomic mass units. If I look up oxygen's mass, well, it's 16.00 atomic mass units. However, since I had two oxygen atoms in the formula, I want to multiply by 2, so 2 times 16. Now, if I add up these masses, 32.07 and my 32, which is 2 times 16, I get 64.07 atomic mass units. This would be the molecular mass or molecular weight for sulfur dioxide. We could also call it a formula mass or a formula weight. So that's one sulfur dioxide molecule would weigh 64.07 atomic mass units. Now, can we weigh that out on the scale? No, absolutely not. We can't weigh a single sulfur dioxide molecule out on the scales in our laboratory. However, if I remember that one molecule of sulfur dioxide is 64.07 atomic mass units, if I actually had a molar amount of this molecule or any formula we're talking about, if I had a molar amount, whatever I calculated as its its molecular mass or its formula mass in atomic mass units would be equal to its molar mass in grams once I have a mole quantity, once I have Avogadro's number worth of those particles, 6.022 times 10 to the 23rd. Okay, so if I had 1 mole of sulfur dioxide, I would have 64.07 grams. Understanding this relationship is critical in the upcoming chapters, so make sure you go ahead and review this when you need to. Now let's consider finding the molar mass for a few other substances. What would be the molar mass of water? Well, first of all, you need to be able to take the name of a compound, which is why we practice writing names and formulas quite a bit before this point in the course. But you need to be able to take the molar mass of water and write the correct you need to take the name of water and write the correct formula. So I'm going to have H2O. Other compounds, I might have to use their chemical names to find the actual formula. Now, if I have 1 mole of water, well, then I can realize 1 mole of water would contain 2 moles of hydrogen atoms and 1 mole of oxygen atoms. So you notice these subscripts tell you about the molar quantities in the formula. So the subscript 2 here tells me 2 moles of hydrogen atoms. If a subscript isn't shown, we assume it's a 1 if it's not shown. So that means I have 2 moles of hydrogen for every 1 mole of oxygen and a mole of water because the formula tells me so. Okay, I should be able to look at any formula and make that same type of reasoning. The subscripts will tell me the molar ratios of all of the element atoms in that formula. Okay, so I have 2 moles of hydrogen atoms for every 1 mole of oxygen atoms. So now I can say that for every 2 moles of hydrogen, I'm going to have a ratio that I can use, which is going to be from the periodic table. I know there's 1.01 atomic mass units on average for hydrogen atoms. If I have a mole of hydrogen atoms, that would be 1.01 grams of hydrogen for every 1 mole of hydrogen. So I'm getting this value from the periodic table from underneath the element. So if I take 2 moles of hydrogen times that mass from the periodic table of 1.01 grams per mole, I get 2.02 grams of hydrogen atoms and a mole of water. But that's not the only contribution here. We also have oxygen present. So if I take 1 mole of oxygen atoms times 16 grams, this should read 16 grams of oxygen here, not hydrogen. So in your notes, change that. So for every 1 mole of oxygen from the periodic table, I see it's 16 grams, right? So I take 16 times 1, that's just 16 in this case. If I add up 2.02 and 16, that's the mass, 2.02 grams of hydrogen for every mole of water, and 16.00 grams of oxygen for every mole of water. If I add those up, I get a molar mass for water that is 18.02 grams per mole of water. Now, what would be the mass of a molecule of water? If I wanted to know the mass of a molecule of water, it's merely 18.02 atomic mass units. See how easy it is to go back between atomic mass units and gram quantities, as long as we think of the gram quantities being related to a mole amount and the atomic mass units being related to a single molecule or a single particle that we're talking about. Okay. Now, water's formula is fairly simple, so let's try looking at a slightly more complex formula. I'm going to look at an ionic compound, so maybe let's talk about finding the formula mass, even though we're using the exact same method that we'd use for a molecular mass. I'm just calling it a formula mass because I have an ionic compound rather than a molecular compound here. So if I want to find the formula mass for calcium nitrate, the very first thing I have to be able to do is use my knowledge of writing formulas from names to come up with the correct formula here. If I'm not able to write the correct formula, I would have difficulty in working this problem. So if you're still having trouble there, you need to review those topics. Now the correct formula for calcium nitrate, since the calcium cation has a 2+ charge and my nitrate ion has a -1 charge, I need 2 nitrates shown in brackets here and a subscript 2 outside. Nitrate's form is NO3-1, so I have 1 cation and 2 anions in the correct formula. Now if I have 1 mole of calcium nitrate, let's consider how many atoms I have in that mole quantity. So if I have 1 mole of calcium nitrate, I'd have 1 mole of calcium atoms. I'd have 2 moles of nitrogen atoms. That's because this subscript 2 affects everything inside the brackets. I have 2 nitrates, which means I have 2 nitrogens, and actually 6 oxygens. Now be careful, as I'm looking at this, I'm multiplying 2 by the 3 to get the 6 oxygens. I'm not adding, so please don't give me 5. Okay, so I have 6 moles of oxygen. So 1 mole of the formula would have 1 mole of calcium. There's a subscript 1 there that we don't show. We have 2 moles of nitrogen atoms because I have 2 nitrates, so that 2 affects everything inside the brackets, including that subscript 1 gets multiplied by 2 to determine the number of atoms, moles of atoms. Now if I have 2 times 3, that gives me the moles of oxygen atoms. So now I know there's 1 mole of calcium atoms in a mole of this formula, 2 moles of nitrogen atoms in a mole of this formula, and 6 moles of oxygen atoms in a mole of this formula. Now the next thing I want to do is go to the periodic table and look up the molar mass for calcium. Now on some of these slides, just to keep everything on the slides and keep things brief, I'm not going to write all the digits. You're going to write down at least to the 2nd decimal place on your piece of paper when you're doing these calculations. I have just written down the first 2 digits because we could fit this all on one slide and let you read it easily. So calcium atoms have about 40 grams per mole for their mass, and I'm getting this value of 40 from looking up at the periodic table and saying, oh, it's about 40 grams per mole. If I had a single calcium atom, it would be about 40 atomic mass units. Okay, now since I have 1 mole of calcium atoms, I can multiply that with 40. I get 40 grams of calcium by mass and 1 mole of calcium nitrate. I do the same procedure for every element. So I go ahead and look at nitrogen. I have 14 grams of nitrogen for every 1 mole. I'm getting this value of 14 by looking at the periodic table. You should be writing out 14.01 to the 2nd decimal place. I've just abbreviated it here. Now, if I have 2 moles of nitrogen in this compound, I take the 14 grams per mole of nitrogen from the periodic table times 2 moles of nitrogen in this specific compound to give me 28 grams of nitrogen by mass for every 1 mole of calcium nitrate. Now for oxygen, what should we do next? Hopefully you said look at the periodic table. What is the mass on the periodic table? Okay, it's 16. So if I have a mole of oxygen, I have 16 grams per mole. And I know that if I have 6 moles of oxygen atoms for every mole of the compound, I need to take 16 times 6. That gives me 96. So I take 40 plus 28 plus 96. So we get a molar mass of calcium nitrate of 164 grams per mole. Okay. Now normally you would have 2 more decimal places here, but I have rounded just so everything will fit nicely on the slide. But we just found the molar mass for calcium nitrate. You should be able to do this for any formula of any compound we talk about. Okay, so you want to practice this quite a bit. I'm going to assume that in the next chapter or 2 you've mastered it and can find molar masses fairly easily. So should we try finding molar masses of a few more compounds? Sure, how about we find a molecular mass? Now formula mass and molecular mass, we find their masses the exact same way. Now if I'm talking about a molecular mass, maybe I'm talking about a molecule. If I'm talking about a formula mass, that really could be an ionic compound or a molecule or any substance we might want to be looking at. They're just slightly different ways of describing the same technique with respect to the type of substances. So let's consider the molar mass of ethanol. Now I have not asked you to memorize the formula of ethanol, so I'm going to give that to you here. It's C2H6O. So there's 2 carbon atoms in the formula, 6 hydrogen atoms in the formula, and 1 oxygen atom in the formula. So if I scale this up to mole quantities, 1 mole of ethanol would have 2 moles of carbon, 6 moles of hydrogen, and 1 mole of oxygen. Okay, so remember 1 mole contains 6.022 times 10 to the 23rd molecules, or atoms, or whatever particle I want to be talking about. Okay, so if I have 1 mole of ethanol, then we would have 2 moles of carbon. I know that from the subscript 2 in the formula. Okay, so 2 moles of carbon. I'm going to look up on the periodic table the mass under carbon and the relative atomic mass is 12.01. If I have mole quantities, that's 12.01 grams of carbon for every 1 mole of carbon. So 2 times 12.01 is going to give me 24.02 grams of carbon in 1 mole of ethanol, which had 2 moles of carbon in the formula. Now, hydrogen, I have 6 moles of hydrogen in the formula, so I can take 6 moles of hydrogen times the relative atomic mass from the periodic table of 1.008 grams of hydrogen for every 1 mole. Again, I'm getting this value from the periodic table. I'm getting the 6 from the subscript from the hydrogen. So I take 6 times 1.008, gives me 6.048 grams of hydrogen for every 1 mole of ethanol. Now, there's only one oxygen in the formula of ethanol, so we're going to take 1 mole of oxygen times its molar mass of 16 grams of oxygen for every 1 mole. Again, I'm getting the 16 from the periodic table. I'm getting the 1 mole here from the unseen subscript that's understood as a 1 after the oxygen. So that tells me there's 16 grams of oxygen for every mole of ethanol. So 1 mole of ethanol has 24.02 grams of carbon in it, 6.048 grams of hydrogen in it, and 16.00 grams of oxygen in it. If I add these all up, I can get a molar mass for the ethanol of 46.07 grams per mole. Okay, so that's going to be my molar mass. Okay, let's try one more. Now you might want to pause the video and try to find this molar mass before I give you the answer for it. This is going to be for glucose, also known as blood sugar. It has a formula C6H12O6. Now, what would be the mass of 1 molecule of glucose, C6H12O6? Now, I look at the formula and I have 6 carbon atoms in every molecule, 12 hydrogen atoms in every molecule, and 6 oxygen atoms in every molecule. So I'm going to look on the periodic table for the mass of carbon, the mass of hydrogen, and the mass of oxygen. I have 6 carbons, 12 hydrogens, and 6 oxygens. So I could take 6 times 12.01 atomic mass units for the carbon, 12 times 1.008 atomic mass units for the hydrogen, and 6 times 16 atomic mass units for the oxygen. So I'm doing this the way we did before, I just didn't set up the same table. If you want to set up the table method, that's just fine. That's a great technique. Now if I add up all the atomic mass units times the number of atoms of each type in the formula, I get 180.2 atomic mass units. Now since I'm dealing with atomic mass units, remember that we're looking at 1 molecule. So 1 molecule of glucose is 180.2 atomic mass units. Now what if I had 1 mole of glucose molecules? Now if I have 1 mole, I have many more than 1 molecule. I have Avogadro's number worth of molecules, so I have 6.022 times 10 to the 23rd molecules of glucose. Okay, so it would merely though be 180.2 grams per mole. So if I can find this value in atomic mass units, I can find it in my molar mass very easily. I scale it up to a mole quantity by converting this to grams per mole. Okay. So remember, when we talk about molecular masses, sometimes we're also referring to molecular weight, or sometimes we'll talk about formula masses or formula weights. They're all synonyms to the same process. The sum of the atomic masses are found from the formula of the compound. We add them up with respect to the number of atoms of each type in the compound and how many are there, and that can find out the atomic mass units for an individual formula or an individual molecule. If I have a molar amount, a mole of it, I'm going to have that many grams per mole. Okay, so first of all, what is the molecular mass of carbon dioxide? So I need to be able to write the formula from the name. So hopefully you recognize that as CO2. Next, I can set up a table to calculate its molar mass. I like to put the type of atom in the table, so I have carbon atoms and oxygen atoms in my table as my first column. My second column, I like to write down the number of each type of atoms. So I have 1 carbon and 2 oxygens. My third column, I like to look at the periodic table and find the masses for each type of element. So here's carbon, so it has a mass from the periodic table underneath carbon of a relative atomic mass of 12.01 atomic mass units. If I look at oxygen, it has a relative atomic mass unit of 16 atomic mass units. Okay, so if I take 1 times 12.01, I get 12.01 atomic mass units of carbon for every molecule of CO2. If I take 2 times 16 atomic mass units, remember I'm multiplying by 2 because there's 2 oxygens in the formula. It's a subscript 2 after oxygen. So I take 2 times the relative atomic mass from the periodic table for oxygen of 16, and I end up with 32.00 atomic mass units of oxygen. Okay, now if I add up the atomic mass units for carbon and oxygen in this formula, I get 44.01 atomic mass units of carbon dioxide. Okay. Now let's see if you can do this for a compound on your own. So let's have a little class quiz. Okay, what we want to find is the molecular mass for ammonium phosphate and compare that to the molar mass as well for ammonium phosphate. So you'll need to determine the formula from its name to get started on this problem. So go ahead and pause the video, trying to find the molecular mass for ammonium phosphate, and then we'll look at the solution of it in a moment. Okay, so now that you've decided on what you think the molecular mass is for ammonium phosphate, let's check your work. So first of all, my molecular mass for ammonium phosphate can be determined by finding its formula first. So I need to determine what type of compound is this. This is an ionic compound. The ammonium cation is paired with the phosphate anion. Okay, if I write the formula for the ammonium cation, I see that it's NH4 with a +1 charge. If I write the formula for the phosphate ion, it's PO4 with a 3- charge. Since the charges are not balanced yet, I'm going to need to have 3 ammonium cations to balance the charge on the 1 phosphate anion, so that I'll have a +3 overall with that -3. So I write this with the ammonium cation in brackets, NH4, brackets with a subscript 3 after it, followed by phosphate, so I have ammonium phosphate. Now, once I have the correct formula, it's very important I have the right formula so I can find the right molecular mass and then molar mass. Okay, so I set up my table, and my first column will have my types of atoms. So first of all, I have nitrogen atoms from my ammonia. I have hydrogen atoms. Hydrogen atoms from my ammonia. And I have phosphorus atoms from the phosphate, and I have oxygen atoms from the phosphate. So there's all the different types of atoms present in my formula. My next column, I want to set up a column that is my number of each atom type. So I want to see how many nitrogens I have in the formula. Now, if you realize there's 3 ammonium cations, that subscript 3 outside the brackets affects everything inside. It means I have 3 of the NH4 +1 cations, which means I have 3 nitrogens. Okay. And if I consider that that 3 also affects the hydrogens, I'm going to have 3 times 4 is going to give me 12 hydrogen atoms in the formula. Now there's only 1 phosphorus, no subscript is shown, so we assume it's a 1. And there's 4 oxygens in the formula. So now I know how many of every type of atom is in the formula of ammonium phosphate. Now the next thing you should have done was set up your column for atomic masses. So I go to the periodic table and I look at the atomic masses for nitrogen, hydrogen, phosphorus, and oxygen. So nitrogen's atomic mass is 14.01 atomic mass units for every nitrogen atom. My hydrogen atomic mass is 1.008 atomic mass units. It's the relative atomic mass for hydrogen atoms. I look at phosphorus. It has a mass of 30.97 atomic mass units. Remember, I'm getting these all from looking at my periodic table, which you will always have during your tests. Then I look at oxygen's atomic mass. It's going to be 16 atomic mass units. Okay, now I need to take the number of every type of atom times the atomic mass per atom to find out the total mass that each element is contributing to the overall formula. So if I take 3 times 14.01, I get 42.03 atomic mass units of nitrogen contributing to the overall mass of the ammonium phosphate formula. Okay, that's because I had 3 nitrogen atoms times the mass from the periodic table. Now, since I have 12 hydrogens in the formula, I can take 12 times the relative atomic mass from the periodic table of 1.008 atomic mass units. That gives me 12.096 atomic mass units. And this should read hydrogen. That's a typo. It should read hydrogen there, so you can cross that out and put hydrogen. Now I have 30.97 atomic mass units for phosphorus. There's only 1 phosphorus atom in the formula, so that's the same value. There's 4 oxygens in the formula, so I can take 4 times the relative atomic mass for oxygen of 16, so I get 64 atomic mass units of oxygen there. Now I can add up all of my masses. If I add up all my masses, I get the overall mass. So the total formula mass is the contribution of the masses from all of the atoms present and the numbers of those atoms present. So my total formula mass, or my molecular mass, if this was a molecular compound, would be 149.10 atomic mass units. Now, if I wanted to know its molar mass, we'll realize the molar mass would merely be if I had a mole quantity, meaning 6.022 times 10 to the 23rd of the ammonium phosphate formulas, I would have 149.10 grams for every 1 mole of this substance. So that would give me my value for both. Okay. Now let's consider this. how many grams of ammonium phosphate would you want to weigh out in the lab if you want to have 2 moles of the compound? Now realize we already discussed that 1 mole of this substance would have a mass of 149.10 grams per mole. It scales up nicely to mole quantities once we go to grams per mole. So I'm thinking about this. If I want 2 moles of ammonium phosphate, and I know the molar mass is 149.10 grams of ammonium phosphate for every mole of ammonium phosphate, meaning when I have Avogadro's number worth of ammonium phosphate formula units. If I take 2 times 149.10 grams, I'll end up with 298.20 grams. So I have to weigh out twice the molar mass if I want to weigh out 2 moles of this substance. Okay. Now the next question I want us to consider is how many grams of ammonium phosphate should you weigh out if you want 1 mole of just ammonium cations? Now you're going to have to think a little bit more about your formula here. If I look at the formula for ammonium phosphate, first of all, how many phosphate ions do we have in this formula? You should note that there's only 1 phosphate anion that was needed in this formula from when we first derived it. However, we had more than 1 ammonium cation. To balance charge with the phosphate, we had 3 ammonium cations. So since I have 3 ammonium cations in the formula, every time I weigh out a mole of ammonium phosphate, I'm going to end up with 3 moles of ammonium cations. So if my problem asks me for just 1 mole of ammonium cations, I don't need to weigh out a whole molar quantity. In fact, I need 1/3 of a mole. Let's set up this calculation with our dimensional analysis. So 1 mole of my ammonium cations, I can recognize that I end up with 3 moles of ammonium cations for every 1 mole of ammonium phosphate. Notice the moles of ammonium will cancel. That's going to give me that 1/3. I need 1/3 of a mole of ammonium phosphate in order to determine how many grams I should weigh out. Now the molar mass of ammonium phosphate is still 149.10 grams per mole. So if I take 149.10 grams per mole divided by 3, because I only need 1/3 of a mole to get 1 mole of ammonium cations, then I need to weigh out only 49.7 grams. Now what if you were to weigh out 149.10 grams of ammonium phosphate? How many moles of ammonium cations would you have then? You'd have 3, right? You'd end up with 3 moles of the ammonium cation. You'd have 1 mole of the phosphate ion. You'd have 1 mole of the entire formula. So I only need 49.7 grams, 1/3 of a mole of the ammonium phosphate to get a mole of the ammonium cation, because there's several ammonium cations, 3 in this case, in this formula. Okay, so that's the end of practicing finding molar masses today. If you have any extra time in class, maybe your on-site instructor could help you practice determining a few more molar masses. Thank you very much. Have a great day, everybody.